Section 4.6 is the content for your homework due on Friday. It's about what are called rates and related rates, especially an emphasis on related rates. And there's lots of practical kinds of problems you can talk about when you think about related rates. Let's start by thinking about problems 36 and 37 here in section 4.6. 36 says gasoline is pouring into a vertical cylindrical tank shaped like a can of radius 3 feet. When the depth of the gasoline is 4 feet, the depth is increasing. They don't put the word rate in there, but you could, at a rate of 0.2 feet per second. Putting the word rate in there is helpful to remind you this is, in a sense, a derivative. It's a derivative not as a function, but as a value. Question is, how fast is the volume of the gasoline changing in the tank at that instant in time? So we've got a cylindrical tank shaped like a can. It's got a radius of 3 feet. It doesn't tell you the total height of the cylinder. It just says when the depth of the gas is 4 feet, at whatever moment in time that is, this is the gas here. Oh, I made it blue as if it's water. Okay, it's not water, it's gas. When the height is 4 feet, the depth is increasing at a certain rate. I guess when the depth is 4 feet, the depth is increasing at that rate. How fast is the volume changing at that instant? You need to use your imaginations. You need to imagine there is a pump here and gas is flowing into this tank. So the amount of gas is going up over time. We have the equation for the volume of a cylinder as pi r squared h. Now that would be the volume of any given cylinder. When I think about trying to solve this problem, though, I want to imagine this equation not applying to the whole cylinder, but to this cylinder of gas. This part. That's a cylinder as well, of height h and the same radius as the overall tank, 3 feet. I could replace r with 3. R squared would be 3 squared is 9, and write this as v equals 9 pi h. Now, a common mistake people make when they try to solve problems like this is they'll say, hey, the depth h is 4 feet. I guess I should plug 4 in here and get a volume of 36 pi. Well, yeah, that would be the volume of the gas at that moment in time, but that's not what you're after. We're not after the volume. We're after how fast is the volume changing. A derivative of the volume with respect to time. You don't see time in this picture. It's in your imagination. V and H both depend on time. They're both functions of time. To find that rate at which the volume is changing with respect to time means I need to find the derivative of V, not with respect to H, but with respect to T. I don't differentiate this with respect to H and get 9 pi. That's not the answer. I assume both V and H depend on T, time, and I differentiate both sides with respect to T. Take d dt, differentiate both sides with respect to T. What do you get? Well, on the left, you just get the symbol dv dt. On the right, 9 pi is a constant. It just stays there times dh dt. I don't know what the functions v and h are, but I don't need to know them to solve this problem. I just use the information that I have. When h is 4, the depth is increasing at 0.2 feet per second. In other words, dh dt is 0.2. Do I ever really need the fact that H is 4 at that moment in time? I actually don't in this problem. It's irrelevant. Sometimes in certain problems, that kind of thing is relevant, but not in this one because I don't see an H in this equation. I just see a dH dt. So now to solve the problem, to find the rate at which the volume is changing at the instant in time when dH dt is 0.2, I just use this equation and substitute dH dt equals 0.2. At the moment in time, I will go ahead and write when H equals 4 feet and dH dt is 0.2 feet per second. I'll go ahead and write both of those things, but we really don't need the 4 in this problem. Again, sometimes some problems you do. dV dt is 9 pi times 0.2, and that'll be 1.8 pi. Get the units right. They'd be units of volume per unit of time, cubic feet per second. The units of the 9 pi are effectively square feet. The units of dH dt are feet per second. Multiply square feet times feet per second, you do get cubic feet per second. It is a rate of change of volume with respect to time. Once again, for emphasis, I never found the functions v as a function of time or h as a function of time. I don't need them. I assume they exist in my mind. That water level is going up, maybe not even at a constant rate. Maybe it goes up faster and faster over time. The gas, I should say, is not necessarily coming in at a constant flow rate. It could be, but not necessarily. So the height could be increasing slowly at first, then speed up, then it could slow down. I could try to find a formula for h as a function of time, but I don't have to. To solve this problem, I only need to know what I'm given. 37, somewhat similar, except now we're dealing with water. Water is being pumped into a vertical cylinder. That would be a tank again, shaped like a can, of radius 5 meters. Okay, now we're going to use standard units. And height 20 meters at a rate of 3 cubic meters per minute. So now you know you're given dV dt. In this problem, you were given dH dt, and you had to find dV dt. In this problem, you're given dV dt, and what do you want to find? How fast is the water level rising when the cylinder is half full? You want to find dH dt. So it's a cylinder again. This time it's got water in it. I'll make it blue. This is literally water now. The radius of the cylinder is 5 meters. And the cylinder itself has evidently a total height of 20 meters. This is a little different kind of information here. Do we need to know that it's 20 meters? Maybe, maybe not. It's not clear yet. The water level height we could call h. That does change over time because water's flowing into it. How fast is that level rising? What is dH dt? When the cylinder is half full, when h is 10, the total height is 20, half full would be 10 meters in height. The equation V equals pi r squared can be used again, times h. And once again, just like before, it's really referring to the liquid, not the entire cylinder. Once again, I can plug in the radius. R equals 5, r squared would be 25, and get V is 25 pi h. Once again, I can differentiate both sides with respect to time and get dV dt equals 25 pi times dH dt. Very similar so far to the other problem. But now, what you want to solve for is different. We want to know dH/dt when we know dV/dt. I could just plug in dV/dt right away here. It's 3 and solve for dH/dt. Or I could solve for dH/dt before I plug in what dV/dt is. I could divide both sides by 25 pi. Keep miswriting that. 25 pi. And then plug in the value of dV/dt. The fact that we're thinking about this when the tank is half full is irrelevant in this problem. Once again, that kind of thing's not always irrelevant. Sometimes the information you have in these problems is relevant, sometimes it's not. It's a problem-solving process to try to figure it out, whether it's relevant or not. When the tank is half full, H equals 10 meters. We can plug in dV/dt was, what was it? 3 cubic meters per minute. I keep writing 2 pi. I'm so used to writing 2 pi. 1 over 25 pi times 3. The H equals 10, again, is irrelevant. I mean, yeah, that is the moment in time we're talking about, when the tank's half full. But it turns out to be irrelevant. You don't have to plug it into the formula. You just plug in 3. Get 3 over 25 pi. This is dH/dt, so this would be meters per minute. Units of time are in minutes here. Probably is more satisfying to approximate that. 3 divided by 25 pi, about 0.038 meters per minute. What, about 4 centimeters per minute? Not very fast. That's right? About 4 centimeters per minute. I think I'm getting that right. Okay. Let's do what would probably be a harder problem. A problem where we're not dealing with a cylinder, say. Oh, but maybe how about a cone shape? A cone-shaped coffee filter. I had coffee this morning. I had a filter. It wasn't cone-shaped, though. Of radius 6 centimeters and depth 10 centimeters, contains water which drips through a hole at the bottom. Really? No, it's more that it's a permeable filter is typically, but okay, humor us here with this problem. Drips out a hole at the bottom at a constant rate of 1.5 cubic centimeters per second. So that would be a value of dV/dt, right? Although because it's dripping out, dV/dt itself, the volume of the water in the cone shape, would be going down. It would actually be negative 1.5 cubic centimeters per second. That kind of thing is important. Various things to do. If the filter starts out full, how long does it take to empty? Find the volume of water in the filter when the depth is 8 centimeters. How fast is the water level falling when the depth is 8 centimeters? Okay. Take these one by one. First, make a drawing. Cone shape filter. There it is. Radius of 6 centimeters. Depth, in other words, height of 10 centimeters. Contains water, which drips through a hole in the bottom. So there's the water. It's also in a cone shape, dripping out through the bottom at a certain constant rate, 1.5 cubic centimeters per second. Part A, if the filter starts out full, How long does it take to empty? That's not really a calculus problem. Figure out the total volume that would fill this filter in cubic centimeters. Divide by the rate at which it's emptying, and you'll get the amount of time in seconds. The total volume of a cylinder, 1/3 pi r squared h, right? You've seen that before. The 1/3 might feel kind of mysterious, but it's correct. 1/3 pi. This is the volume of the filter itself. R squared would be 6 squared. H would be 10. Right? Radius of the filter is 6. Height is 10. 6 squared is 36. Times 10 is 360. This is 360 pi over 3. This simplifies to 120 pi cubic centimeters. Somewhere close to 400 cubic centimeters. 120 times pi, 377 cubic centimeters. That's probably good to use. Oops, sorry. About 370, I'll go 6.99 cubic centimeters. So the time to empty is approximately 376.99 cubic centimeters divided by 1.5 cubic centimeters per second. The cubic centimeters cancel, giving us the amount of time in seconds. Divide this by 1.5, you get about 251.3 seconds. And what would that be? A little over 4 minutes. Next part, part B. Find the volume of water in the filter when the depth of the water is H centimeters. H, a variable, not specified. Well, it's still a cone. What is the moment in time when this happens? We're not saying. It's a general moment in time and a general height. I got to find the volume. I guess I need to figure out this radius right here. It's got to depend on H, right? How? A couple different ways it could be found. You could use similar triangles. I'm purposely drawing a vertical line in here to make a couple right triangles in the picture. If you want to redraw it, you can. This is H. That's R of H, function of H. That's 10. This is 6. These two right triangles, the big one and the small one, are similar to each other. They both are right triangles and they both share this angle. By that similarity, you can say the ratio 6 over 10 equals the ratio R of H over H. This reduces to 3/5. You can solve this equation for R of H. It's 3/5 H. That equation, I wrote it with function notation. I didn't have to. I could have just called this R instead of R or H, which is kind of abusing notation as it is. Could have just called it R. R is 3/5 H. You also could have figured that out by just thinking about it in terms of the fact that R of H has got to be a linear function of H and equal to 0 when H is 0. When you got no triangle, when there's no more water, R is 0 when H is 0, and equal to 3/5 when, or equal to 6 when H is 10. If you graphed R as a function of H, its graph looks like this. And the slope of that line is rise over run, 6 over 10, which is 3/5. That would be another way you can figure it out. We're after the volume now. Volume is 1/3 pi r squared h, but now replace r with 3/5 h. Right? Is that what they say to do? Find the volume of the water when the depth is h. Yeah, they wanted you to find it as a function of h. Replace that r with 3/5 h. You get 1/3 pi times 3/5 r or h squared times h. The volume as a function of h, I'll write an f of h here. Simplify this. 3 squared is 9, divide by 3 gives you 3. 3 pi, h, or the 5 gets squared down there to give you a 25. H cubed, h squared times h. 3 squared is 9. Divide by 3 is 3. Got the pi. 5 squared in the bottom is 25. H squared times h is h cubed. That's the answer to part B. Part C. How fast is the water level falling when the depth is 8 centimeters? So the water's level is going down. dV dt is negative 1.5 cubic centimeters per second. You don't see a negative sign up there, but it is dV dt being negative because the volume is decreasing. The water level is going down. But the question asks, how fast is the water level falling? We actually want a positive answer here because of the word falling. If the word falling was changing instead, then we'd want a negative answer. The water level is going down. It's changing, decreasing, negative derivative. But it's also falling, so because of the word falling, we actually want to take the absolute value of our answer. But in terms of derivatives, think about that with negative signs in the end here. Assume both v and h are functions of t. They are. The water level is going down. In fact, h is a very simple function, or v is a very simple function of t. It's a linear function of t. I won't find its formula, but you don't have to. Differentiate both sides with respect to t, assuming v and h depend on t. This is very similar, though not exactly the same, to implicit differentiation. You don't see any t's here. It's in your mind. Assume v depends on t, assume h depends on t. And when you differentiate this side with respect to t, you do not get 0. You also do not get 9 pi over 25 h squared. Instead, you get 9 pi over 25 h squared times, by the chain rule, the derivative of the inside function dh dt. That's the chain rule that I used there. I assumed h is a nice differentiable function of t. And when I looked at this expression with that kind of idea in my mind, I said I need the chain rule because h as a function of t is the inside function. The outside function is the 3 pi over 25 h cubed. So that's what I start to write down. But then I don't have an x there or a t, I have an h. It's just a function of t. That is the inside function times the derivative of the inside function. That is the chain rule that I just used. Again, this is very similar, though not exactly the same, as implicit differentiation, where you assumed y was a function of x. Here we're assuming everything is a function of t. These are called related rates problems because we're relating rates. How about that? Related derivatives. Are we done? No. How fast is the water level falling? How fast? What's dh dt? When the depth h is 8. That's relevant here. I need the fact that h equals 8 because you see an h in this equation. I could plug in the numbers right now. I also could algebraically solve this equation for dh dt as 25 over 9 pi times 1 over h squared times dv dt. I could do that. I just divided both sides by 9 pi h squared. I also multiplied both sides by 25. Not that you have to do that, but you should be able to. Now plug in your numbers. Plug in h equals what? It was 8 centimeters. So I get an 8 squared. dv dt, what's dv dt? It's not 1.5. It's negative 1.5. Which is the same as negative 3/2. If I want my answer as a fraction, can I do all this? I'm going to get a negative, what? 3 times 25, 75. 8 squared, 64. 64 times 9. 64 times 9, and also times 2. 1152. Don't forget the pi. Units would be centimeters per second or minute. I forgot. What's time? Per second. Okay, that's going to be a small number. 75 divided by 1152 times pi. About negative 0.0207 centimeters per second. It's not the final answer, though, because the final answer is how fast is it falling? Take the absolute value of this. Absolute value of this is positive 0.0207 centimeters per second. And you would want to do that because of how the question is phrased. How fast is it falling?